I want to tie loose ends, so to speak, today, finish few items, few subjects from chapters up to 30 that have to do with magnetics, or magnetostatics, to be precise. Magnetics or magnetostatics, because we really did not study magnets in this course, right? Magnets is a different world. Magnets is a world that I don't think anybody understands what happens in it. But that's not what we want to, what we've been studying. We've been studying what we call magnetostatics, meaning that there will be magnetic field that will be generated based on a DC current, And up till now, we've been idealizing things. Things have been idealized. What do you mean by idealized? It means that we made approximations and assumptions to make our life a little bit easy. But eventually, right? Eventually you say, why should I keep making things easy? Eventually I want to do something useful, right? So how long has magnetism been, how long has it been known? It had been known since what? People theorize since the Greek times or before, right? If you go to Wikipedia and look at magnetism. So the history is quite old. What about electrostatics? Old, right? I think it goes back to the Greeks. You take amber or you take some dielectric and you kind of rub it under your shoulder and then you hold. Remember, you bring it closer to pieces of paper and you lift them up. Those were very, very old experiments, or I should say observations. But since what, a couple of thousand years ago or even more, some people say the magnets go back to the Chinese who first discovered them, not the Greek. So we're not going to have a national, you know, if we have Greeks in this, taking this course, I think they will object to that. Nevertheless, my point here is this, is not to give you a historical perspective, but to tell you that for thousands of years, thousands literally, we've known what? We've known electrostatics and magnetostatics. But did we make anything useful out of them? Not to my knowledge, possibly. In other words, have people engineered something useful out of magnetostatics and electrostatics? Possibly, possibly. Maybe scientific observations, but nothing useful has been made until the late 1800s. Okay, so yes, Volta and others lived prior to 1700 in Rome, in Italy, but they really never made something really, really useful out of them. Useful in a significant way to have a major impact. So until Faraday came along, this man was smart. He was really a cool guy. But I thought of motivating you as I was coming to the lecture today. So what's so special about all of a sudden, thousands of years, and all of a sudden, someone comes up with something that drastically changed everything? Literally, drastically changed everything, because today's world as we know it, as far as the technology in it, is based on Faraday's law. Is that an exaggeration? No. So the first revolution, the first industrial revolution, there was something revolving that created that revolution. What was it? The motor, right? And then the second revolution, the wireless revolution, is based on what? Faraday's law. Isn't that amazing? So when people say that he was one of the most important experimental physicists of all times, that's not an exaggeration. So in terms of impact, but so what is important lesson for us The important lesson is that he made observations. Okay, he made very, very important observation. So do you think he's the first one ever to observe a needle flipping if there's a changing magnetic field next to it? I don't think so. It sounds impossible that he's the only one to see that. But he was very sensitive to say, wait a minute, I've seen this happening every time the magnetic field is changing, I see the needle flipping. This cannot be a coincidence. Okay? So you guys have to really, I mean, the lesson from this is that one has to be very, very sensitive to what you see around you. If you're very sensitive to what's happening around you, then you can actually create knowledge, right? You can create knowledge. But if you pass by, it doesn't matter. You know, you just pass by things, okay? Then you're really not creating knowledge, okay? That, in my opinion, is the motivational or the inspirational part of Faraday's work. Okay, so we're gonna get into that very soon, today maybe, if we have enough time to cover the few things that I want to finish off before we start Faraday's law, because Faraday's law ties everything together, ties electrostatics and magnetostatics, and we end up with something called, or what we call electromagnetics. So no longer can we talk about electrostatics alone or magnetostatics alone. I'm going to start this way and walk my way this way because of the light here. All right, so let me finish a few things. And the first one I want to talk about is an example. Is not just any example, but it's a generic example where I assure you, you might find something similar to it in the final exam. So what is this example? I want to find B due to a current. I want to find B, magnetic field, find B due to a current loop. Okay, the current loop. What is the current loop? The current loop, I'll use a different color here, orange. First of all, I center my space. This is the center of my space. It's going to be like this. So this is radial line. This is an arch. And this is a radial line. So it's basically two arches, okay, connected with these radial lines, okay? So this is the problem. Clear to everyone? This line here can be represented by constant angle. This line can be represented by constant angle because it's a radial line. This line is a radial line, so it can be represented by a constant angle. What do we mean by representing a line by a constant angle? It means that if I am walking on this line, what are the coordinates that are changing? The radius, exactly, just the radius. The angle is fixed, okay? Similarly here, if I walk along this line, the angle is fixed, the radius is changing. What about this line here? Well, you have to take my word that this is a constant radius, okay? And this is a constant radius. So let's say this one has a radius of R1, and this has a radius of R2. Okay? So if I walk along this line, what happens? What are the variables that change? Is R changing if I walk along this? No. R is fixed. Is the angle changing? Yes. Similarly here. Okay? This represents a generic type of loops. Okay? We can try to trick you by making different arrangements that will making different loops that are composed of arches and radials. Okay? So let's go on and find the B. So the B here is mu naught, I follow the template, 4 pi divided by 4 pi, integral of I dl crossed with r hat, and divided by r squared. Now, this is integrated over the current path. I like always to represent my problem like this before I put actual numbers. What is missing from this question? What is missing? I didn't tell you where to find the magnetic field, right? I have to tell you, find the magnetic field at this point. So for this problem, I'm going to find the magnetic field right here. Someone asked me last lecture, what do you mean by observation point? Observation point is the coordinates of the location where we want to find the magnetic or electric field. Okay, so I'm not going to go over this in details. It's in the notes, okay? You can see it, but I want to point out a few things. First of all, when we have a current path like this, first of all, there's something not right here. This should be in the other direction, right? Otherwise, the current is playing games on us, right? Going this way, and then we can switch this way. Or I could have switched the other ones, okay? But the point is that I have to have a current going in one direction. Otherwise, it's impossible, right? In AC analysis, that's a different story, but right now. How do we create this? Well, we cut this and put a battery here. That's how we create the current. But for all practical purposes, I can take the voltage source out and analyze this. So this one, I'm integrating over the current path. So what is this R here? This R, so if I'm, let's say here, if I'm over this, R is the vector that is pointing towards the what? The observation point, right? So it is pointing in that direction, R hat. R squared is the distance between here and here squared. So I don't want to write everything because IDL here, for this particular segment, IDL is pointing in that direction, in the negative phi hat direction. I take that and I cross it. I take this and cross it with R hat. This, cross it, this, crossed with this, what will I get? Something up or down? One more time. Phi is going in that direction. R is going in that direction. So I take the right-hand rule. Let me see if I can do this. The right-hand rule, 1 out, sweep it towards the R, you will get what? Inside the board, right? Inside the board. In other words, if you want to think of it mathematically, one vector, both vectors that I'm crossing are in this plane. Okay? This plane is the xy. So let's say this is x and this is y in the Cartesian, or r and phi in the cylindrical. I take the phi crossed with r, I will get inside, which is negative z. Correct? All right. So what about, so I can continue integrating over all of this here. And I do something similar here. The only difference is that IDL here is pointing in the opposite direction. Okay? So it's pointing in the opposite direction. So if I take phi, cross it with r, which is pointing in that, I'm going to get a vector that is pointing out of the board. Okay? So what about along this one here? Here, r is pointing in this direction. Correct? R is pointing in this direction, and IDL is pointing in the same direction. So for any segment that you take here, R is pointing in this direction, and IDL bar on top of it is pointing in the same direction. So in other words, for these generic type of problems, don't waste your time integrating over everything. Here, there's no contribution due to this part. and there's no contribution due to this part. The only contribution is due to this part and due to this part. Okay? There are two types of problems that we're interested in as far as calculating the magnetic field. Okay? One is we give you a loop. I want you guys to look at the big picture. So to realize that, yes, we're covering different things, but they're generic type of problems. Here, we're giving you a loop. I give you a loop, and I ask you to find the magnetic field. Okay? There's another type of problems where I give you the magnetic field, and I ask you to find the current, the integration of that magnetic field over a certain contour to find the I inside of it. Okay? This is a generic, the first type of generic problem that we're talking about. So I end up integrating over this, okay? Whatever that is, you look at, I'll just give you the final answer because this integration actually is quite easy. The R here is constant. Whenever I integrate over this, I integrate between this angle here, whatever that angle is, and this angle. R is constant, so this R squared is constant. Turns out to be a very simple integral. R squared is constant. This and this will give me minus Z for C1, let's say, C1, and this is C2. So I have integral over C1 plus integral over C2. Okay? Similarly here, this one, for C2, the angles are the same. I'm integrating between this angle and this angle. R for C2, R is constant. It is radius number 2, R2. And you integrate between these two angles. So the final answer for this one turns out to be quite easy, actually. It's a simple geometry. So my mu naught I divided by 4 pi, mu naught I, 4 pi, the angle, I wrote it in two different ways. Let me see. I wrote it in a very compact way, okay? In a very compact way. Here, phi sub A, and then I have 1 over R1 minus 1 over R2 Z hat. So that's the final answer here. Okay, the last thing I need to tell you what is phi A. Phi A is phi 1 is this angle. This is phi 1, and this is phi 2. So phi A is phi 1 plus phi 2. Okay? The reason I chose to give you this, I think this example is also available in the book, but it's also in the notes. The reason I gave you this, because once you realize that you're not integrating over the radial directions, the problem becomes simple. Notice, if I were to ask you to find the solution right here, it is not as simple, right? It becomes actually quite complex, right? We can play all kind of games with these geometries. Yes.
Is there a general formula for the electric field at the center due to a ring of?
This is magnetic field. You mean magnetic field?
Yeah, magnetic field due to a ring.
There can be. It's possible. It's possible. I cannot think of.
I think there should be a negative there because the total, it should be negative Z, right? Negative Z hat.
No, this is correct. 1 second. This is correct. This is correct. The only difference which, no, this is correct.
Because we have a small radius R1 and then minus the bigger radius R2.
R1 is the smaller radius,
I mean,
right?
the more powerful field lines it's 1 over R1 and it's pointing in the negative direction of
The first one,
yeah, this one is
the field is higher.
and it's higher than the other one.
Okay, let's do it very carefully. So when I integrate over this, I am dividing, I have a field that has 1 over R1 squared, correct? Over R1 squared. And when I integrate over this one, I have 1 over R2 squared. R1 squared is smaller, right? R1 is smaller. No, I think this is correct. I'll look into it. I'll look at the.
Can we not use the equation for the circular loop that you gave us last class or a couple classes ago?
No, because we're not. In what sense?
Like you could find the field due to a complete circle, but then divided by the portion that that arc is of the complete circle.
But that was a difference because that loop that we took before enclosed a current.
No,
I mean, but this is quite simple. I don't know why we need to simplify it any further than this. This is quite simple, right? Let me show you, if I were to, actually I can use this one here. Someone asked me a question about Ampere's law last lecture. If I had a current that is coming out of the board, okay? So this is a current that is coming out of the board, which means that I have a dot here. So this is I. Will it create, it creates a field that we know what that field is. We've solved it before. B, let's say this is the angle phi. B is mu naught divided by 2 pi 1 over r, right? And there's a phi hat. Does that look correct, guys? Yes? The decay, one more time. I is coming out. The field everywhere is looking like this. The decay is 1 over r. It's not 1 over r squared. Remember, I keep saying that the analogy between electrostatics and magnetostatics is not perfect. Do you see that? But look at the formula for B here. Look at the formula for B. B decays as 1 over r squared, right? B decays as 1 over r squared, which looks similar to what we had for the electrostatic case. Remember electrostatics, the field decayed as 1 over r squared. Do you see the parallels? Why, when I come to the infinite, guys, let's focus on this. We can discuss other things, but I don't want you guys to miss this. This is important. If I have a current that is infinite in that direction, I'm not having a decay of 1 over r squared. Be very sensitive to the things we discuss. Be very observant, okay? This interesting observation is very important when one develops numerical codes to predict the magnetic or the electric field. The problem with this picture, because everything in life, all forces in life, as far as I'm concerned, decay as 1 over r squared. Why this is not decaying as 1 over r squared? Well, B is related to F directly. So we expect this to decay as 1 over r squared. The problem, not the problem, the idealization we use is that the current is infinite. Is there such thing as infinite current? No. You see? So if you had an infinitesimal current by itself, then you will have a different kind of decay. All right? The other thing I want to say is the following, about following up on Ampere's law. This field is everywhere, correct? Everywhere. It's not zero anywhere, correct? It's not zero anywhere. So who asked me this question at the very end, right? So if I were to have this loop and I were to integrate B over this loop, what will I get? 0. Is it intuitive? No, not to me at least. It's really powerful. No matter what loop you take, as long as it is outside the current source, you're going to get 0. Okay? Don't confuse this with calculus when we integrated a function between 2 points or from 0 to infinity. If I integrate a function from 0 to infinity, and any function that I integrate, if I get a 0, okay, any generic function, I integrate it from 0 to infinity. If I get a 0, that tells you that this function must be 0. That's not the case here. Do you see that? So in other words, I can give you a different loop. Look at this loop here. I can go and give you a loop like this. The integration of B is always 0. Okay? And how to prove that? Can we prove that? We can do it using the same argument that I used before. What is that argument? I divide any curve into arches and radials. Any curve, I divide it into arches and radials. Okay? All right, that's it for this discussion. Okay. And again, I'm wrapping things up in this lecture, tying loose ends, so to speak, so that we start fresh tomorrow with electromagnetic fields. We discussed last time the solenoid, right? This is the solenoid that we discussed. And we found that the field inside is almost constant. If the solenoid is finite, what will happen? We will have B field that is going to fringe like this. So it's going to be straight coming from one end and feeding into the other end. If I have a loop like this, a solenoid, very tightly packed, and I have another one next to it, what do you expect to happen? They will attract. They will lock into each other. Why? So this has a magnetic field that is coming out like this. I should use other colors. So this has a magnetic field, B, that is coming out like this. And this, let's say the winding is the same and the direction of the current is the same. So it will have a magnetic field that will be similar to this, right? Why would these two attract? Why? We've seen this before, right? You solenoid. We use a solenoid as a switch, right? The clicking in old cars, when you do something, there's something clicking. It's a switch that basically closed using a solenoid. That's why we hear the clicking sound. Modern cars don't have it. Why do they attract? Why do they attract? Is it? Why do they attract? Because you have a hat, that's why I picked on you.
F is equal to QV, QV cross B, right? And then we can make the QV somehow to I. So the field, the magnetic field attracts the current of the other.
Okay, so to answer this question, we need to go to the very first formula we learned, the force due to a magnetic field, the force acting on a charge. I want to be very precise. This is important. The force acting on a charge moving in a magnetic field. Okay? The force acting on a charge moving in a magnetic field. And let's try to remember this. The force acting on a charge is QV cross with B. Remember this? Force acting on a charge moving in a magnetic field. Magnetic field created externally. There's a charge moving. There's a force. So the charge will be bent. There's a force that tries to move it. Okay? If that Q is moving in a presence of a magnetic field. Okay? So how does that help us understand this? Yes?
So we've completely moved away from statics now? Like everything can move now? Are we
Magnetostatics.
everything is
Magnetostatics. DC. DC current.
So charges are allowed to move now?
That's how we develop the magnetostatic theory, is that the charge is moving with a constant velocity. Right? Did I deviate from this, guys? Right? We said it from the very beginning. Q is moving with a constant velocity. It creates a magnetic field.
So is it accelerating it?
No.
But if it's changing velocity, like if
No, it's not changing velocity. It's constant velocity. I said it's moving with a constant velocity. The charge is moving with a constant velocity. Like me, I'm moving with a constant velocity. Okay? It creates a magnetic field. Okay? Remember, we started with a charge which is not moving. Create electrostatic. Charge is moving. DC creates magnetostatic. First one creates an electric field. The second one creates a magnetic field. All right? Okay. So there's a force. So the easiest way to look at it is that I'm going to take one loop only, and I'm going to cut. So the loop is coming out of the board like this. I'm going to chop it like that so I show you the current that is coming out and the current that is coming in. Do you see that? Like you take a ring. I'm going to put the ring orthogonal to the board. Okay? I'm going to chop it like that. And now you look from your perspective. You see only a current that is coming out and the current that is going in. Is that clear? All right. Now, this part here, will create a magnetic field. Actually, the loop, we solved the magnetic field due to a loop. Remember? That was the second example we did. If we have a loop, what is the magnetic field along this axis? We solved for that, right? So now I have a magnetic field that is everywhere in the world due to this one. Okay? If I just take this incremental, this element here, it's going to create a B that is either going this way or going up, depending on the direction of the current. This current is coming out. The current is coming out. R is going in that direction, so I can put the R vector here. The current is coming out. IDL cross R. IDL is like that, cross R, so I'm going to get a B in that direction, correct? Right? Because this one is coming out, so you can use the right-hand rule. We just did it one more time, okay? So there's a B that is going in that direction. This, I'm going to put another loop right here, just like this one. Loop, the same direction. The current will have the same direction coming out, going in. The current here is coming out. IDL is going in that direction, or QV is going out. QV crossed B. QV is this one here, right? QV for the second loop is coming out. Is that clear, guys, or should I repeat this one more time? This gives you a B. This current will give you a B here, right? Now I'm going to put another loop here. Fair? Same as this one. I'm going to put an identical loop. So 2 rings, 1 ring and another ring. Okay? Now I'm going to look at the current that is moving out of this ring right here, or through the ring. This current is QV, is a Q moving with a constant velocity. I take that, cross it with B, which is generated by the first one. Now I'm going to get a force that pulls this towards the first one. Now, if you do it with 2 rings, the force is not that much. So that's why you need so many rings. I borrowed a big battery. It's in my office, and I'm going to try to do an experiment. And if it works, you guys are going to see it. If it doesn't work, you're not going to see it, OK? The battery is a heavy-duty battery. It's like a car battery. Yeah. So, because for the solenoid, you need a lot of current. OK? Yeah, you need many loops, and you need strong current. Okay? And these experiments are usually not that friendly. Yes?
Where's our head like pointing to this? Like
One more time, speak up.
where's our head like?
OK, I wanted to find the B due to the current here. OK, so R hat, this is the observation point, right? This is the observation point. R is pointing towards the observation point. OK, so that's why R is going in that direction. OK, so you take R, the B that is generated by this is going up. So you take that R, cross it. No, the R was used just to find the B. OK, I didn't need to do that because we solved the field due to a current source, right? But now once I know B, I need to be aware of the direction of the current on this on this second loop. The current is coming out. So in conclusion, if the currents are going in the same direction, these 2 loops will attract each other.
So this is like some, like if you go like however many loops down, like they're all getting summed by figures.
Each one will have its independent. We can perceive it as having its own independent current. So it's going to increase the B. It's going to increase it linearly, actually linearly. OK? Now, the tricky part is the following. So far, so good. So the tricky part is to generate this force between these 2. OK? I'm generating a force. It doesn't come free. It doesn't come free. What did I spend to generate that force? Current. I had to feed a lot of current, right? I had to feed this one and this one, both of them. I had to feed these loops a lot of current to make them attract. So why then, the question, why would 2 magnets attract each other? So this, what we've created here, we created the effect of a magnet, north pole, south pole, south, north. That's why these attract. It makes a lot of sense, doesn't it? We developed the theory very, very carefully. We believe in what we're doing. Okay? We did it faithfully. And we right now see that these 2 attract. But why, if I have 2 magnets, north, south, north, south, why would they attract? Are we feeding energy into it? It's a mystery. It is a mystery, right? One day, you guys will solve these. One day, maybe, one day you will say, what you guys taught us was nonsense. Remember the Bohr atom model? I mean, the quantum people say, what is that nonsense, right? But in 1910, I don't know the exact year, it was what? The hottest thing in the world, right? The Bohr model. So one day we might discover that the models that we are doing do not satisfy us, and it's not that they were wrong, okay? It's not that they were wrong, but they did not give the full picture. There's a difference between being wrong and they did not give you the full picture, okay? Let's say, like the Earth. Remember when people thought the Earth was flat? Were they wrong? Well, locally they were correct, right? Locally it was flat. But the more you add to your model, meaning the more physics, the more information, you will say, wait a minute, it's locally flat, but not globally, okay? I'm trying to clean up their image, those idiots, right? Who thought the world was flat. All right, so I'm going to show you something very, very interesting next time here that follows up on this. Okay, I'm going to do something very quickly, and I might not be able to finish it, but if I don't finish it, you can look up the notes, okay? But at least start the discussion on the concept of a DC motor, okay? We did not talk about it earlier, and I don't want to spend too much time on it because some of you actually had it in high school, okay? So the idea, okay. The idea is that we have two wires here, and I have I1 going through this one, and I have I2 going through this one, okay? We've established right now similar arguments that we've done here, is that if the current is going in the same direction as this one, and let's say these are parallel, then there will be attraction force between them, okay? So these try to come closer to each other. And similarly, if I1 was going in an opposite direction to I2, they will try to actually push each other, okay? So one more time, actually I don't need to repeat it, it's right here, F equals QV cross B. We are making simplifications, we're making assumptions. What are the assumptions that we're making is that I is moving in free space. So there's no aluminum, no copper, no iron. It's moving in free space. When you put the I on inside copper or aluminum or some metallic material, the phenomenon is not exactly what you see here. So I, in this wire of length L, I, is the Q in it. This is a review of something we did before the midterm, the resistivity discussion. Q divided by delta T, okay? I is the Q or delta Q divided by delta T. dQ dt will give you I. What is Q? Q is L divided by V. L divided by V. V is the velocity of the charge, okay? So this equals QV divided by L. L is the length of the wire. So we can right now represent the force acting on this wire, okay, as the magnitude of the force, as I'm going to put QV right here, okay? So instead of QV, I'm going to have substitute for QV Li. Li. Since I'm interested in the magnitude, I simply multiply it by B. So this will be Li B, okay? All right. So this is a useful way to express the force when we have two parallel wires. Now, I'm going to, in the last 5 minutes, I'm going to discuss the concept of the DC motor. So I'm going to take a rectangular loop. This is a rectangular loop, okay? And it has an axis here, Z. This is, I'll try as much as possible to do this. Right. So B is a magnetic field due to an external, it's an external magnetic field, and then I insert a current into this loop in that direction, okay? So this has a length of L. All right, so this is a perspective view looking from this side, looking from here towards the loop. I see something like this. This is the loop. You can see the loop if you're looking from that direction. From this direction, you see only a line, okay? So if I were to stand on this line here that goes through the plane of the loop, I'm going just to see a line, okay? And the B is pointing in that direction. So this is the external magnetic field, B. B is pointing in that direction, okay? So what is happening here? I have an eye that is coming out here, this in this direction, which means that it is coming along the element that is going in this direction, an eye that is going in that direction. So if we have a QV, I or an I, meaning that I have charges going in that direction, in the presence of a B that is going in that direction, there will be a force. This I crossed with this B will be a force going up, right? Going up. So in other words, this part or this wire or this segment of the loop will experience a force pushing it this way. Similarly, this portion here, which has a current going in, will experience a force going down. Okay? I'm not going to write all the math, very simple, it's in the notes, but let's understand the concept here. This B is going to create the fact that there's a current going in the loop, and in the presence of B will create a force that is trying to torque this loop upward, okay? So if the loop, this is the loop like this, okay, this is the surface, the cross section or the surface enclosed by the loop, it's going to torque it this way, okay? It will stop if the loop reaches this position, correct? Because right now there will be zero force on the top and the bottom legs or parts of this loop, correct? This part and this part experience no force. Okay? Why? This part, the current is going in that direction. The current going in that direction, cross it with B, you will get a force going in that direction. So in other words, this part of the loop, there will be a force pulling it out. This part of the loop, there will be a force pulling it in that direction. So it's not going to do anything. Otherwise, it will be deformed, okay? So the only thing for this loop to do is to flip or to be torqued this way. It will stop here unless we do something interesting to keep it turning, okay? perpetually, forever, right? Now, this is an idealized model. This is how the DC motor is built. Just give me half a minute and we'll stop. This is how the idealized motor, DC motor, works. Soon we will find out that this is not a complete picture. Why? Because the B, you see, the B that crosses this surface, okay? So remember, this was the surface enclosed by the current, okay? There's not much B crossing it. If I were to start with a surface like this, how much B is crossing this surface? We call it flux, the total flux, magnetic flux, just like electric flux. Okay, the total B that crosses the surface is called the flux. How much is crossing this? 0, right? Because B is parallel to it. There's nothing going up. How much is crossing it? Maximum, right? So as I go from here to here, the B, the net magnetic flux that goes through the surface is changing, okay? This will change the picture completely. That will create, guess what? That will create a new kind of current in this loop. And that will lead us, this is a very nice, actually, logical transition to Faraday's law. So for the first time, whenever we start moving things, electrostatics and magnetostatics take a back seat. All right? So tomorrow we're going to start with Faraday's law until the end of this term. Yes?